Hi, my name is Dominik Fuchsgruber and I'm a PhD student at the Data Analytics and Machine Learning group at the Technical University of Munich. And I'm very excited to present our latest work on uncertainty for active learning on graphs. Applications in machine learning are often limited by their data efficiency. We study active learning in the context of interdependent graph data. That is, we query an oracle iteratively for additional node labels. The goal is to optimize the model performance with the least amount of queries possible. A popular acquisition strategy is uncertainty sampling. There we select the node that the model is most uncertain about for labeling. Our work investigates the efficacy of this strategy for node classification problems. The total predictive uncertainty of a model is typically disentangled into two facets. On the one hand, there is aleatoric uncertainty, that is inherent to the data. Examples are measurement errors or label ambiguities. It cannot be reduced in general. On the other hand, there is epistemic uncertainty. It originates from a lack of knowledge, such as unseen novel classes or insufficient data in general. It can be reduced by, for example, acquiring additional training examples. We approach uncertainty from a Bayesian perspective by considering the data generating process, which, of course, may be unknown in practice. Given some set of labeled nodes, we define the total predictive uncertainty of a model inversely to the marginal probability of a prediction giving all current available labels, which are denoted by a blue capital L. Similarly, we define irreducible aleatoric uncertainty based on the corresponding marginal if we now had access to all the other node labels denoted by a capital U. In this case, there is no additional information to be gained, and all remaining uncertainty, therefore, must be aleatoric. Note that in practice, we do not have this information about these unlabeled nodes. Following the well-established notion of uncertainty being additive, this implicitly defines the epistemic uncertainty as the difference between the total and the aleatoric uncertainty. With these definitions at hand, we can state the core result of our paper. We can show that querying the label of the most epistemically uncertain node is an optimal acquisition strategy. It maximizes the confidence gain in correctly predicting the classes of the remaining unlabeled nodes. What does that mean exactly? Let us look at this graph. For each unlabeled node, there is an uncertainty, or equivalently confidence, with which the model predicts the correct class. Selecting the node with the highest total or aleatoric uncertainty may increase the model's confidence in correct predictions to some degree. We now show that labeling the most epistemically uncertain node will result in the highest increase in this confidence among all possible queries. Put differently, epistemic uncertainty sampling will optimally push the model toward correct predictions. We first verify this result on synthetic data, where we have full knowledge about the generative process. We compare uncertainty sampling using either the total predictive uncertainty or the epistemic or aleatoric uncertainty to a baseline of random queries. In line with our theoretical findings, we observe epistemic uncertainty to be the most effective proxy. We also observe that it is crucial to remove aleatoric factors as they negatively affect the active learning performance. Additionally, we ablate uncertainty that is computed from an inaccurate generative process and find that while it too has negative implications for effective uncertainty sampling, overall the disentanglement of uncertainty plays the more important role. Computing epistemic uncertainty according to our definition as the difference between total and aleatoric uncertainty is challenging. That is because the computation of these quantities relies on access to the data generating process, which is typically unknown for real data. Additionally, aleatoric uncertainty relies on labels of node that are not in the training set. We mitigate these issues by using GNNs to approximate the predictive marginal. We assume this to sufficiently model the generative process implicitly. Furthermore, we can use its predictions as surrogate pseudolabels to compute aleatoric uncertainty. We now evaluate this approximate framework on real graph datasets. First, we consider existing uncertainty estimation approaches and find that they often struggle to outperform random queries in terms of data efficiency. In contrast, our generative framework enables highly effective active learning. We apply two different approximative algorithms for epistemic uncertainty as we define it, and find that both outperform all competitors. This validates our perspective on uncertainty and the implied optimality result. Both seem to generalize well to real-world problems as well. Overall, the core insight of our work is that for active learning on graphs, uncertainty sampling using epistemic uncertainty is an optimal strategy. We verified this claim both on synthetic and real data. This points to various directions for future research. First, we observed the disentanglement of epistemic and aleatoric uncertainty to play a crucial role in effective uncertainty sampling. While our approximate algorithm shows strong performance, we rely heavily on approximations and conjecture that more elaborate methods may perform even better. One ingredient for such novel methods can potentially be an accurate notion of the data generating process that so far is mostly only implicitly modeled by training a GNN for classification. Lastly, we believe that our theoretical analysis can provide useful insights in other domains as well. Especially for non-IID problems, our generative lens may guide the development of highly effective active learning strategies. If you want to know more about our work, we would be very happy to see you at our poster. Also, don't forget to check out the project website using the provided QR code. Thank you for your attention.